Hi everyone, today we'll talk about 99% revenue with constant enhanced competition, and this is joint work with Raghuvansh Saxena. One of the most important problems in algorithmic game theory is how do we design revenue maximizing auction. In our setting, there are n bidders and m items. The items are independent and identically distributed, drawn from a prior distribution D, which is also a product distribution over the items. The bidders are additive, which means that their value for a set of items is just the sum over their values of each individual item. Given the distribution D, our goal is to design a truthful mechanism that maximizes the expected revenue. However, revenue optimal auctions have many undesirable properties when there are multiple items. For instance, it might get less revenue from bidders with actually higher values. It might sell lottery tickets for sets of items instead of just giving them deterministically, and it might be computationally intractable by many measures. So ideally, we would like to use an auction that's simpler than this optimal auction. But how good is a simple auction? Well, a long line of work has established that simple auctions can indeed achieve a constant approximation to the optimal revenue. However, this approximation ratio is often unsatisfactory, especially for high-stake auction settings where losing more than 85% of the optimal revenue might be undesirable. What we really want is to get 1 minus epsilon fraction of the optimal revenue just with a simple auction. And can we do this? This will be very challenging to do in the traditional setting. However, we can do this with enhanced competition. In this paradigm, we want to find the number of bidders n prime, where a simple auction with n prime bidders almost matches the revenue of the optimal auction with n bidders. So what's the motivation here? The motivation is that if n prime is not much larger than n, then we can conclude that instead of spending so much effort designing this optimal auction, we can instead spend more effort recruiting the bidders. So the focus of our paper will be on resolving the question on constant enhanced competition. Basically, is it possible for the augmented number of bidders n prime to be big O of n? On this slide, I'll show the progress on the constant enhanced competition problem, for which n and m is the constant enhanced competition enough to get almost full revenue. So the first result is by Bloor and Klemperer 1996, which says that when there's only one item and when the distribution is regular, then with only n plus 1 bidders, a simple auction can get almost even more than the full revenue. And next, Feldman, Friedler, and Rubinstein 2018 and Behadi and Weinberg 2019 proves that when there is only one bidder, or when the number of bidders is much larger than the number of items, then constant enhanced competition is enough. In fact, when n is much larger than m, the effect of competition is so much that even with the original number of bidder n, a simple auction already gets almost full revenue. So in this setting, the enhanced competition is not doing much here. So what about this upper triangular part where m is much larger than n? Prior to our results, only super constant enhanced competition is known in this setting. And our results completes the story on constant enhanced competition by showing that for all n and m, regardless of whether they're constants or how they relate to each other, constant enhanced competition is enough to get almost full revenue. So specifically, what we prove is that a simple auction with O of n over epsilon bidders can obtain a 1 minus epsilon fraction of the optimal revenue with n bidders. And note that this 1 minus epsilon factor is also not necessarily needed in all of our cases. So what we prove exactly is that at least one of the cases hold. There are two cases. Either a second price auction with n prime bidders gets at least a 1 minus epsilon fraction of the optimal revenue with n bidders, or the case 2 holds where a simple auction with n prime bidders generates even more revenue than the optimal auction with n bidders. In fact, this more revenue part can be replaced by c times more revenue for any c that is a constant. So we haven't really talked about what the simple auction is, and this is because it doesn't really matter. In extension of our theorem 1, we actually prove that case 2 holds for any auction that guarantees a constant approximation to the optimal revenue. So we have to note here that in fact it is necessary for like an auction to guarantee a constant fraction of the optimal revenue if it were to get near optimal revenue with constant enhanced competition. And our theorem 1 can be interpreted to saying that this is sufficient as well. So now we have finished discussing theorem 1, we'll move on to our next theorem, which concerns the case where we might not know all the information about D. So we will propose a prior independent auction that generates almost optimal revenue with constant enhanced competition. So first of all, what we'll do is that we'll modify theorem 1 such that the case 2 here is prior independent. Our theorem 2 says that when items are regular, either this case 1, which is the same as in theorem 1 holds, or a prior independent auction with O of n over epsilon squared bidders will generate 1 over epsilon times more revenue than the optimal auction with n bidders. However, note that the theorem 2 is still not prior independent because we have to differentiate between case 1 and case 2 in order to assign the appropriate auction. Fortunately, we can fix this issue by using a hybrid auction. In the hybrid auction, we'll run the auction in case 1 with probability 1 minus epsilon, and we will run the auction in case 2 with probability epsilon. So note that if case 1 holds, then the hybrid auction gets 1 minus epsilon times 1 minus epsilon, at least 1 minus epsilon squared fraction of the optimal revenue. On the other hand, if case 2 holds, then the hybrid auction obtains at least epsilon times 1 over epsilon, which is equal to 100% of the optimal revenue with n bidders. So in conclusion, if for the hybrid auction, no matter which case it holds in theorem 2, the hybrid auction with n prime bidders will obtain at least 1 minus epsilon squared fraction of the optimal revenue with n bidders. So for the rest of our talk, we'll talk about the proof for theorem 1, and the proof for theorem 2 will follow a similar outline. So our proof will be as follows. We'll first assume that case 1 in the theorem 1 does not hold, and we'll try to prove that case 1 does hold, assuming case 1 does not hold. Our step 1 will be proving a related claim to this case 2, which says that a simple auction with n prime bidders generates more welfare than the optimal welfare with n bidders. Note that in the theorem, the keyword is revenue, but in step 1, the keyword is welfare. In step 2, we'll generalize the claim in step 1 to virtual welfare. And in step 3, we'll finally use an established connection between optimal revenue and virtual welfare to conclude the theorem. So let's first start with step 1. The lemma says that assuming, as we said, case 1 does not hold, which means that second price auction with n prime bidders extract at most 1 minus epsilon fraction of the optimal revenue with n bidders. Assuming this, we want to prove that the welfare with n bidders is at most 1 over 20 times the welfare with n prime bidders. And here, n prime is equal to 20n over epsilon. So this lemma actually holds for multiple items. However, here we'll only prove for the special case when there's only one item because it already contains all the main ideas. So let us consider the case where there are in total n prime bidders. This n prime is equal to 20n over epsilon. And the first n bidders here will participate in the second price auction. So what is the expected welfare from these first n bidders? In the second price auction, the expected welfare is just the expected highest value amongst these bidders for this item. And so now there are two possible cases. Either the highest values amongst these first n bidder is exactly equal to the highest bidder overall amongst these n prime bidders, or that is not the case, then the highest value amongst the first bidders is at most the second highest value amongst all n prime bidders. So since the value for these bidders are independent and identically distributed, we can see that this first case where the first n bidders, the highest among the first n bidder is exactly equal to the highest overall, has a probability of n over n prime, which is epsilon over 20 of happening. And with remaining probability, case 2 happens. So now, note that the expected second highest value with n prime bidder is exactly equal to the revenue from a second price auction with n prime bidders. And by the lemma, this is the assumption in the lemma says that this is at most 1 minus epsilon fraction of the optimal revenue with n bidders, which is less than equal to 1 minus epsilon times the expected welfare with n bidders. Now that we have reached this step, just by a rearrangement of terms, we conclude that epsilon times the expected welfare with n bidders is at most epsilon over 20 the expected welfare with n prime bidders. Dividing both sides by epsilon concludes our lemma for one item case. And for the multiple item case, we simply need to sum over the items for these terms. So now we have been done with step 1. Before we prove step 2, we're first gonna assume that step 2 is already true and see what is the connection between optimal revenue and virtual welfare. So Kai, Devanner, and Weinberg 2016 proposes a definition of the multiple item virtual welfare. Note that this is different from the Myerson virtual welfare for the single item case. Then, for this definition of virtual welfare, they prove that the optimal revenue for n bidders is at most the expected virtual welfare, which is then at most 8 times the revenue from a simple auction. So, ideally, for this definition of the virtual welfare, what we want is that we can generalize the lemma in step 1 to virtual welfare, where assuming that case 1 in the theorem does not hold, then the virtual welfare with n bidders is at most 1 over 20 times the virtual welfare with n prime bidders. So why is this useful? This is because by combining CDW16 and this modified lemma, we can prove theorem 1. So let us see how we can do this. Firstly, by CDW16, the revenue from n bidders is at most the virtual welfare from n bidders. Next, by our modified lemma, we know that the virtual welfare from n bidders is at most 1 over 20 times the virtual welfare with n prime bidders. So finally, we use CDW again, and this says that the virtual welfare from n prime bidders is at most 8 times the revenue from a simple auction with n prime bidders. Since 8 over 20 is at most 1, then the revenue from n prime bidders is at most the revenue from a simple auction with n prime bidders. This is exactly what we need to show in theorem 1. So now, step 3 is also done. And the only thing left for us to do is to prove step 2, where we want to generalize the lemma in step 1 to virtual welfare. So now let us see if the definition of virtual value from CDW will make this modified lemma hold. So what they define the virtual value as is as follows. So the virtual value for bidder I and for item J is equal to the Myerson virtual value if bidder I gains the highest and non-negative utility from item J in the second price auction. Otherwise, the virtual value will be equal to the value, and this is how they defined it. So now let's see if this will make the lemma hold. We discovered that, okay, so here is the virtual value in indicator form. And we discovered that for any virtual value, the lemma will hold as long as the following conditions hold. So first of all, the virtual value must be at most the corresponding values, and then the distribution of the virtual values for different bidders must be independent and identical. Finally, the distribution of virtual values must not depend on the number n of bidders participating in the auction. So the CDW virtual value definitely satisfies the first condition because it is either the value or something that's at most the value. This is true. However, the second and third conditions are all false. This is because, as you can see here, the virtual value is actually dependent on the value of the other bidders. So the virtual value for different bidders is definitely not independent of each other. And since the total number of bidders is n, this distribution is also dependent on n. So what do we do now? Of course, we want to modify this virtual value so that it will satisfy these conditions. So our first idea is that in order to remove the dependencies between virtual value of different bidders, instead of using, the other n-1 bidders value as a proxy, we will instead draw n-1 ghost bidders and take the expectation over their values. So we'll take here the modified virtual value, we'll take the expectation over this v minus I that is drawn from this distribution. And let's see if the conditions now are all satisfied. So the first condition is still satisfied since the virtual value is a linear combination of this value and then something that's at most value. For the second condition, since we already removed the dependency between the virtual value of different bidders, now this is also satisfied. However, the last condition is not satisfied because the distribution of v minus I is still dependent on n. Our next idea is that we're going to fix some very large number n prime larger than any number n that we care about, and we'll draw n prime minus 1 ghost bidders instead of n minus 1 ghost bidders, and then take the expectation according to that. So now, since we removed the last dependency on n, all the conditions are now satisfied. Finally, we must do a sanity check. We started with CDW16. This is our foundation. We must check that for this modified virtual value, CDW16 still holds. And we're not going to get into the detail here, but this turns out to indeed be the case. So now we have completed all steps in the proof for Theorem 1. In conclusion, we showed that for all m and n, an arbitrarily large constant fraction of the optimal revenue from selling m items to n bidders can be obtained by simple auction with all of n bidders. Prior to our result, when m is much larger than n, only super constant results are known. There are still many interesting unresolved questions in this paradigm. For instance, can we obtain full instead of almost optimal revenue with all of n bidders? Or can we obtain almost optimal revenue with small of n additional bidders? Or if this is not possible, can we prove a lower bound? We'll be very excited to learn about the answers to these questions in the future. Thank you very much.